Hey guys, so lesson 3, cyclic hydrocarbons. We'll just continue on with our notes from here. So basically when we make a cyclo, so we're taking a chain. So I can't really show all of them using my kit and models just because of the rigidness of the plastics. But basically when you take a alkane, or you can do an alkene or a kyne, of course, as well. So let's say we have pentane, and if we took each end and put them together, okay, we'd end up getting a structure like this. So this would be called cyclo 1, 2, 3, 4, 5 pentane. So cyclopentane, this nice pentagonal shape that you can see here. So what you should have noticed is that, let's pretend I had my hydrogen chain, or sorry, my carbon chain. And what I'm going to use is I'm going to take some pieces, little balls on the end, to represent the hydrogens that would be attached. Now remember, every single end of these would technically have a hydrogen on it. Now, if I were to take my end pieces, okay, and I'm just going to use the reds to mimic the hydrogens that I'm taking off. So this would be C5H12, which would be, CnH2n plus 2, so that's your alkane formula. You take off your two hydrogens, 1 and 2, and then you would put them together, the end pieces together, to make your cyclopentane. So cyclopentane would be an isomer to cyclopentene because of the removal of those two hydrogens. All right, yeah, we can go on from there. So it's a closed carbon chain. It's alicyclic. Going back to our day 1, we had our alicyclics, alicyclics, and then our aromatics, which we'll be learning about next in our benzene. So the general formula is the same again as an alkene. It's an isomer, and I just explained why. For naming, same thing. You find your longest chain. It can be an alkane, or an alkyne, because you can have double and triple bonds in your cyclos. Same thing with naming. All that we're doing now is adding the prefix cyclo in front. And for branches, they start on, one of them is number 1. So I'll explain what that means. Basically, where do you start? Because it's a circle. So you say, okay, my branch is here. That's number 1. All right. And then again, it's an ene or an ine. If they become carbon number 1, that's your lowest number. So the enes and ines take precedence over the chains is what they're saying here. So you find your double or triple bond if it's there, and then that would be your first carbon, and then you'd go on from there. And then you can either go clockwise or counterclockwise depending on what's going to give you the lowest number for all the other functional groups that are present. So for example, if there's a chain on it or another double or single bond. Okay, I think that's all I had on that slide. Yeah, cool. Okay, so let's do some examples. Let's look at cyclobutane. So cyclobutane would actually just end up looking like a square if we were taking out the, if we were doing the line diagram. So this really is just this. And then, of course, we'd have our two hydrogens on the end of each of these guys. And I'm just writing them on this side because it's easier with the lineup. So these are cyclobutane. It's an ane because we don't have any double bonds there. Now, if we were to look at this structure, this would be cyclopropane. And I could actually put a methyl group here and here. So because I have 2 of them, I'm going to start over here or here. Doesn't matter. If I start here, I would say that this is 1 and this is 2, okay, instead of going 1 and 3. So this would be 1, 2 di, remember, because there's 2 of them. Methyl, cyclopropane, and remember it's propane because we have 1, 2, 3, and ane because there's no double or triple bonds, so all single bonds there. Okay, alrighty. So let's go over here And let's add a double bond here. So the double bond is between this carbon and this carbon. So this would just be cyclo propene. And the reason why I don't need to have a number in front of it is because it's always going to be a number 1 if there's only one of them in it, okay? So you could technically say cyclopropanene, but I forgot to mention this on the other days, that if you don't see a number, you always assume it's the very, very first carbon, okay? It's kind of like saying X in a math question. You don't always put 1X because you know the one's there. It's the same idea as when you're naming your hydrocarbons, okay? So it's assumed that it'd be 1 if you don't see a number there, okay? All right, let's do another example. Let's look at a little more of a bigger structure here. So sometimes you may see a branch written like this. And really what this is it's just an ethyl group. Instead of writing CH2CH3, you just combine it to be C2H5 because it ends up being the exact same thing. And then we have another one down here, okay? And then we're going to put this as C3H7. Now the question is do I start here as number 1 or here as number 1? So the general rule of thumb is alphabetical order in this situation because it's a circle, so you don't know where to start or which end is going to be the best to go from. So we're going to start over here and label this one number 1. So this would be number 3, okay? So this would become 1 ethyl, 3 so ethyl because there's 2 carbons, 3 propyl, and then cyclohexane. So on the first carbon, there's a 2-carbon chain branch. On the third carbon, there's a 3-carbon branch, and it is a cyclic 6-carbon single bond only structure. So there's your whole name for it, 1-ethyl 3-propyl cyclohexane. Okay, so those are just some examples to start you off. Alrighty, so if you're following along, again, there's more examples that I gave you in your lessons. So you can keep following along with that. Some more chemistry jokes for you. You've been in organic chemistry way too long. Every time you see a stop sign, you shout cyclooctane because it's a octagonal shape. So that's your little joke. I know I'm reaching pretty far with these, but we got to keep the entertainment alive with that. All right, so let's look at our organic halides. And halides, remember, think of your halogens, so that's group 17. They form really easily with organic compounds because the fact, if you think about their electron dot diagram, they have 7. So they're searching for that 1 electron, and it's really, really easy for them to bind with carbon because, again, carbon has that 1 spot open on all 4 sides of it for that. So that's why they're so prominent in these, and they're really easy for them to connect with them. Okay, so basically some of the examples that we have, CFCs, chlorofluorocarbons. You may have seen these, the sticker for these in your refrigerators or your air conditioners, and this is one of the reasons why they can be deemed bad for the environment. Your freons, sometimes they're called freon or freon 12 and stuff, they definitely have been contributing to the destruction of the ozone layer. So that's especially why when we dispose of electronics and technology and appliances, that it's important that we do it in the right and safe way so that they're not going into the landfill, getting into the atmosphere and causing problems. So Teflon, right, that no-stick pan that you have, that you cook with. So that would be polytetra. So remember, so poly is a polymer, tetra 4. So 4 fluoros on a carbon. So basically your carbon chain is going to have 4 of the fluorines substituted there. Insecticides. So for those of you that took Bio 20, we talked a lot about DDT, and the name for DDT. So the full name for DDT, dichloro. So 2 chloros. So 2 chlorines. substituted. Diphenyl, so phenyl is actually a functional group of when benzene becomes a functional group. Tri, so 3 chlorides on an ethane. So the structure for that, again, you can actually start to determine what, or start to visualize what the structure would look like. PCBs, polychlorinated biphenyls, again, so that phenyl group's coming up and the chlorine's coming up again. Electrical transformers, again, trying to make sure that we dispose of those correctly when needed. So we name it as we name our branches just as we normally would, and continue on from there. And fluorines become fluoro, chlorines become chloro, bromide becomes bromo, and iodide's a little different, it just becomes io. So we drop everything and just leave the io on it from there. All right, so let's look at our first example. So we have CH3Cl. So we start with our carbon in the middle. We're going to put our hydrogens around it. And one of our hydrogens is substituted with chlorine. So this would be called chloromethane. It's still methane because of the one carbon that we have with it. Let's move on to the next one. So start with our carbon in the middle, as we always know, because it has the most bonding sites. We're going to put 2 hydrogens around it, and then we're going to put our chlorines as well. So this would be dichloromethane. Now, sometimes a question comes up is, does it matter which line you put your chlorines on? I happen to put the hydrogens on opposite ends and chlorines on the opposite. But what you're going to notice is it doesn't actually really matter which one you have it on. So I'm going to use 2 different colors to show you guys this. So let's pretend that my green is chlorine. Okay. And my red are my hydrogens. So it doesn't really matter where they go, because right now we have, you know, the greens are opposite and the reds are opposite, but then as soon as I switch it, now they're on the same side, and so on and so forth. So it doesn't actually matter where it goes, if it goes up or down or side to side in these cases, for high school chemistry, of course, because they're really the same structure. They're just rotated or manipulated around, okay? All right, so let's go to the next one. So we're going backwards on this one. This one we're actually starting with a name and we're making the structure. So 1,2-dichloroethane. So now it becomes important, not if it's going up or down, but which carbon the chlorines are connected to. So it says dichloroethane. So we start with our ethane, and it says 1,2-dichloro. So that means that on the first and the second carbon, we're going to have a chlorine group substituted on here. And then the rest, of course, are my hydrogens. All right. And the reason why that's important to have that 1,2 is because we don't know if the 2 chlorines are both found on this carbon or if they're found on number 1 and number 2, because that is a different substance, and it has definitely different chemical properties and things like that. For those of you that go on to take university chemistry, you'll learn about the stereochemistry, which is basically exactly where the chlorine is. Is it you know, in the top or the side or whatever it may be. 2-fluoropropene. So for this one, we're going to start with our propene. Okay. And it doesn't really matter if I'm starting, well, I have to start from this side because of the double bond, but it's always going to be in the middle anyway. So 2-fluoro means that on the second carbon I have a fluorine group, and then of course at the end I fill in my hydrogens. Now make sure when you fill in your hydrogens that you're actually counting your bonds, because chlorine, or this carbon already has 4 bonds, so I cannot put any hydrogens there. This already has 2, so I can only put 2 hydrogens left here for that, okay? So there's your answer. And I know those of you that actually took, or sorry, all of you took Chem 20, that technically our shape would look a little more like this. Okay, and again, we have that fluorine on the second carbon kind of thing from there. So, yeah. Awesome. All right, so let's move on. There's a few more examples that I gave you guys in your follow along lesson that you have filled in. So there is our chlorine. Here's our another little science joke. 1,2-dimethylcyclopropane, the bikini bottom molecule. Do I have more jokes? Oh yes. Yes, I do. Okay, things I learned from organic chemistry. I love this one, how to draw a perfect hexagon. So in university chemistry, it's really heavily based on that. Remember we were talking about that boat and that chair configuration on our last lesson? So lots and lots and lots of hexagons. It's the basic shape. And I apologize, I didn't show you guys the actual meaning behind that boat and chair configuration. So if I were to actually make that's a penta. So if I were to actually make my cyclohexane, okay, these are like Legos for adults, are super fun. Not saying adults can't use regular Legos. So here would be your boat configuration, because these, just basically this carbon, the attachment here would both be going up. And then the chair is when you flip it like this so that it's coming down. So when we're talking about chemical properties and how they react, that is actually starts to become important when you're actually looking at this stereochemistry of the molecule. And there's your cyclopropane. So it says under too much stress and probably should have fallen apart, but somehow I'm still here. The reason why that joke is the way it is basically, it's a good example when I show you with my guys. Now, the reason why I started with pentane is because the fact that these are very rigid, and I'm not going to break my substance, but basically if I were to try to make cyclopropane, I actually have to add a lot of energy to make it. So I literally have to almost force them, and I'm not going to because I'm going to bend this, but you have to really put it under a lot of stress to get that configuration. So it says it's under too much stress and it should have fallen apart, but somehow still together. All right, and there we go. I'll see you guys tomorrow for your next lesson.